Thanks for the introduction, Sydney. Yep, my name is Peter Hopton. I'm the founder of Icetope and I'm the dissemination and exploitation lead for EuroEXA. And I have the pleasure of presenting to you in this afternoon's siesta sessions here in Valencia. So, first of all, a little bit about the route to ExaScale here in the EU. In 2015, the EU awarded the first H2020 related ExaScale projects. There are about 14 of these, each receiving less than 10 million euros, and they were subject area focused. So you had some looking at storage, some looking at networking, some looking at nodes, multi-chip modules. You're going to hear a little bit about some of those today as part of the presentation, because some of those fed in to EuroEXA. In 2017, with the start of the first co-design projects, there were 2 awarded. EuroEXA is the largest, and EuroEXA received around 20 million euros of EU money, but then a large amount of additional value was pushed into EuroEXA. I'll tell you a bit more about that in a minute. We then have expected first ExaScale demonstrators in 2019-2020, and a first ExaScale machine turned on in 2023-2024. So the ExaScale demonstrators, the expectation there is you're looking at systems of probably around 40 to 80 million euros worth of cost that demonstrate something that's going to be at least on a trajectory to ExaScale, or something that's ExaScalable. Now, when it comes to ExaScale, I think everybody in the room kind of has a bit of a perspective on what that's going to be. But I put this slide in because I go to many places where it's either up for debate or not understood at all. But I think the interesting thing here is 10 to the 18 flops or equivalent. And I kind of think of that as when you see a job application, it says a bachelor's degree or equivalent experience. Obviously this is the gold standard, but actually, is there going to be something else that's going to be more economically relevant in terms of actually solving real-world problems? And I think one of the focus of the direction that we're taking in exploitation out of EuroEXA is, how do we solve real-world problems? How do we deliver economically moving forwards? So, or equivalent is actually very important to us. The EU is expected to buy 2 systems, one from an EU-only consortia, or at least with a lot of EU-based technology developed within it. And they're spending significantly in NRE as part of Horizon 2020 programs, and now the EuroHPC initiative, which has a research and development portion of it. It's also expected there's going to be some pre-ExaScale machines as they're described. These are going to probably be in excess of 100 million euro. I'm hearing even these could be in the couple of 100 million euro each number. But a lot of this is still up in the air with the recent founding of the EuroHPC initiative. And of course, when it comes to ExaScale, there's a lot of big challenges between where we are today and where we need to be to deliver an ExaScale machine. Things like programming models, resilience and reliability, supply chain, scalability. I've got one here: latency, cooling, density and distance. They're all actually intertwined. And one which I'm going to talk a bit more about, which is associated with that, is energy effectiveness. I try not to refer to energy efficiency within computing, because computers are 100% efficient at producing heat. They produce compute as a byproduct of that, or a waste product of that, I suppose. So I prefer to think of this, performance out of a computer as energy effectiveness. How much waste product are we getting from these 100% efficient heaters? So energy effectiveness is something that's quite important. So, EuroEXA. There was a large call and an open competitive exercise organised by the European Union. And the winners for that were a number of partners, and a number of partners that came from 3 of these projects, which were in the previous calls, the 2015 ones that I spoke about. The subject matter area specific focus. And we got a large amount of IP and EU funding, and that formed EuroEXA. This is a €100 million slide. If we look at the total of the IP, the feed-in, the EU funding, and these feed-in projects, and we look at what's on this slide, it's €100 million. So this is by no means a small project. The objective was stated on the EU Cordis as a 4x improvement in energy efficiency and a 4x improvement in performance. These are the organisations that were selected as part of that process and formed a consortium that won the bid. A number of commercial partners here. As you know me, I'm from Icetope. We've got academic and government partners here. Soon going to be hearing from Paul, he's from Barcelona Supercomputing Centre. And then we have a number of supporters here that supported our bid and support us on an ongoing basis. Now, energy effectiveness. Everybody in the room has heard of Moore's Law, I'm absolutely sure. Up until this point, who in the room had heard of Kuhme's Law? Give me a show of hands. Got a couple. And who in the room had heard of Shannon Hartley? Okay. So, at the moment, you may have noticed there's a bit of a trend going on with chips getting hotter and motherboards getting smaller. Liquid cooling's coming back in. This may offer an insight into why. Could be a way of explaining it. So, Moore's Law was this: the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. And here we go, all the way back to 1900, all the way up to Titan X there, and that's our laws, our Moore's Law line. I don't know why it's called a law. It's not a law. It's an observation of a trend. Therefore it can't be dead ever, because the trend may stop, but the observation of the historic trend still exists. So, I don't know. Kuhme's Law, again, another observation of a trend. Dr. Kuhme, who's at Stanford, I believe, he made the observation that in the history of computing hardware, the number of computations per joule of energy dissipated has been doubling approximately every 1.57 years. They're kind of tied together. We've got more transistors on a chip, we've got more energy efficiency. So effectively the chip's operating in a similar thermal envelope. We've got more transistors, thermal envelope equals electrical power energy. And there's Kuhme's Law illustrated nicely there. Now, Shannon and Hartley, these guys were from Bell Labs in the 20s and 40s, and they have a little formula here around bandwidth with respect to signal power and noise in a channel. We could start to think about this actually as how much energy is required to transmit a bit of data. That formula can be turned round. So given a particular channel of copper from A to B, there becomes a physical limit as to how low you can go in terms of the amount of energy to transmit data. And that's, consider that a ceiling on energy required to transmit data. So if Kuhme's Law holds good, and we've got twice as much data for the same amount of energy every 1.57 years. What happens when Kumi's law starts to run into that real law of physics? There. And that's what's happened. That's what's causing this trend. This is a nice little illustration from the University of Manchester. Did this, and it shows 2008 in blue, 2018 in red. I'll just move this very slightly, sorry if you did so. This axis, we've got energy, and on this axis we have distance. So what you can see is, well, there's 10 years of Kumi's law at work. We've got a dramatic reduction in energy for producing the data in the first place and transmitting that data around the chip. Now, when it comes off the chip, we have an issue here. 10 years and very little progress because it's hit that real law of physics. And then over here, we've got improvements on optical. Optical isn't bound by that same rule. In fact, in many occasions, people talk about exceeding Shannon Hartley limits on optical connections. And we're seeing an improvement in optical trends, but note that optical's still a good order of magnitude out from copper. And that's why if you buy a Mellanox switch, it's got a really, really big power supply at the back of it, which often you won't use if you connect it up with copper. It will use a lot less power than the power supply in the back of it. When you plug those optical modules in, they get quite hot and consume quite a lot of power. So here, in the middle here, we've got that limit. And what we're seeing is the memory, which if we all think back to a motherboard 10, 15 years ago, was probably the processor was here and the memory could even be over here on a card somewhere. Or the processor could be on a card, quite far apart. And then things start to move closer together. Also, processor to processor connectivity used to be relatively far apart, and now they're moving close together. In fact, they've moved so close together now that processor to processor connectivity on a two processor system, one sits in the other one's heat shadow on a lot of Intel motherboards. That's not something you do, generally without having really good cause to do it. Because if one's in the other's heat shadow and you've got air blowing past the first one, the other one's getting exhaust air. So you must have good cause to do it. And then the memory moves from being off to one side to being split around the processor. And then most recently we're seeing memory now moving on to the processor package and calling it high bandwidth memory. Well, guess what? Its bandwidth's better because it's not got so far to go and it's got a limited amount of energy. And so the package temperatures are going up. Not temperatures, power emissions. The number of watts from those packages are going up. So we're seeing trends where the processors of today and the future are in the hundreds of watts, 200 to 500 watts being projected within different pipelines. So the knock-on effect of that is that to do really high performance computing, we need to kind of redefine high density. We need to look at how much can we connect together really close together, generally within, it's about 50 centimeters, that break-even point between copper and optical. And then after that, how can we then tie all those together and put them so that they're compact, so that factors such as speed of light that were mentioned in the last presentation don't get in the way too much. And one thing that was put to me was, could we do 60 megawatts in less than a 40 meter maximum run distance from one computer to the other? And that's been a little bit of a target for us that's been in the back of our minds on how we could achieve that, and we think we can. So, next 3 years of EuroEXA, in trying to get to show that we can do that, we've put a test bed in to Manchester that's installed. This is providing a relatively small number of nodes for software development. We've got a second test bed going in that's providing hundreds of nodes. I think eventually we're hoping for around 500 nodes in this test bed. And that's going to allow us to show new infrastructure technologies and test that scalability and that density. And then a third test bed where we'll be testing new node and processor technologies that will ultimately deliver ExaScale. So about getting that 60 megawatts into a 35 meter diameter. Well, if you think about a compute cabinet, at the moment you've got a whole load of space wasted at the front because of air intake, a whole load of space wasted at the back because of hot air coming out the back, exhaust. And inside, you've got a bunch of cables blocking that airflow. So you've got to think about how you're going to tidy those cables. The cables come out and then they've got a bend radius. You use up lots of space, waste a lot of space. We took the concept here of totally liquid cooling everything, removing air from the heat transfer equation inside of the facility and backing the cabinets to the wall. And this means in a modular container, we can have rows of cabinets against the wall and then an aisle up the middle. And what we can effectively have with this container is we can have a hot end. I don't think physically hot, I'm thinking in terms of data hot, where the servers end, and we can have a cold end where there's facility. Power provision, transformers, heat rejection apparatus and things like that. And then we can stick all the hot ends into a circle. We can stack these things 3 high, and we can fit all of our distance critical IT within a radius like that. And in doing this, we're looking at about 2 megawatts per shipping container. And it's been shown to be potentially achievable, but it's something that hasn't been done before, not at this sort of density. So we kind of think about this as turning it up to 11. 100 kilowatt cabinet, it needs liquid cooling. We've been using OCP Open Rack because it gives us some extra inches around the side that would normally have been wasted. And we get rid of this wasted space. And we've been using distributed DC power that enables us to consolidate the power supplies. We found that if we liquid cool the power supplies, that we could make a power supply that would be conventionally designed for a smaller power conversion capacity in air, increase its power conversion capacity because it's better cooled. So we're able to look at power conversion in the region of 20 to 30 kilowatts a U for taking from AC to DC. And then inside, these are what the server trays look like. A number of modules. These are Com Express sized modules. And there are 16 of them in a 10U server tray. At the rear, there's heat exchange and pumping of a server level coolant that goes around this like a dishwasher. It's the best way to think about how this works. The coolant goes around it like a dishwasher. Everything gets wet, but nothing's swimming. And at the front here, we've got the management controller, and we have the QSFP cages. Now notice, we've taken the QSFP cages and we've rotated them through 90 degrees so the cables are coming out sideways. We did that because that enabled us to get rid of the bend radius on the cables and the QSFP cage sticking out the front. And that itself saved us about 10 centimeters of cabinet space. And it's that then enables us to put this into that container. So to liquid cool these dense cabinets, we need some clever technology, and I've spoken a bit about this dishwasher, this immersion without submersion. Because immersion tanks are very inefficient, they're not very serviceable, there's issues. And airflow, well, we've spoken a bit about the issues around airflow. You can also take heat away from your liquid cooling. Liquid cooling likes working at 45 degrees centigrade. Data center airflow likes working at 27. So if you mix the two, they fight each other. So we've been looking to operate a 45 degree inlet with a low risk cooling system using fully fluorinated coolants that are non-flammable, inert, non-toxic, non-conductive, and also importantly have a low dielectric constant, because one of the things with all these high-speed signals, dielectric constant's becoming a big problem. And in the facility level cooling system, we have a sub-atmospheric system running there, because that system uses water. And the last thing you want with a half billion euro supercomputer is to spring a leak. This is TED. TED is our thermal proxy, extra high density test environment. And I'll show you TED running in a minute, but this enabled us to test heat loads of the future before we even have processors that get that hot. And there's 4 kilowatts in a 10U box here. If the technology gods are willing. Oh, well, something went wrong there, but if we all kind of put our heads on one side. I'm hoping you'll be able to glean from this is that you have a small amount of coolant coming out of nozzles. It fills up in these heat sinks here and flows along the circuits. So it's not immersed, but everything's getting wet. And there's kind of a concentrator around the hottest heat sources that concentrates coolant around those heat sources and helps spread the heat out. And this enables us to achieve 47 inlet, 55 outlet at 3.2 kilowatts per U.
So essentially you're looking at a full motherboard cover?
Everything. Okay. And these are actually daughter cards that sit on a carrier. And so if you imagine there's a base load of coolant inside of there that's flowing, and you've got things like DIMMs sticking off the bottom of these daughter cards that are then actually in coolant. And then there's a board that they're plugging into, and that's got various things in, and there's other boards plugging into that. So, although this looks like it's just one layer of PCB, there's actually stack-ups of PCBs in there. And those stack-ups of PCBs mean that we can get something really, really dense and put everything nice and close together. Helps us take advantage of the Shannon Hartley units. Nodes. So, we've got this thing which we're going to call a co-design recommended daughter card. We've had a co-design triumph. Those who've seen my presentation before will know that this is a co-design project, and that co-design projects are fantastic things because they let us cut through waste. Very often people like to sit within their silos. Within our project there's a swear jar. It costs you 20 euros to say that's a hardware problem, or that's a software problem, or that's someone else's problem that isn't in your silo. With co-design, what we look to do is make sure that applications through to infrastructure are in some way joined up in considering the impact of decisions they make upon each other. And within the project we had a daughter card, and it was identified that if we move from the daughter card we had to a slight variation of the design where it was effectively the same resource but 3 separate FPGAs were consolidated into a single multi-chip module, it would improve our performance in most applications by 4x. That's so dramatic, you just have to do it. So this here is your first sneak preview of a co-design recommended daughter card, where we have a large FPGA accelerator, and we have a small MP SoC that effectively is the host that boots the card. And then we have a large number of high-speed links coming off of these devices that then connect to each other and enable also connecting to other devices, such as if we wanted to, we could put an ARM processor card in there, or a Xeon in there, or we have a modular infrastructure that enables that. So with things like EPI, if EPI ends up with a positive result, we can take EPI-based devices, put them onto a module, install them, connect them to these accelerators. The idea is this is a modular infrastructure that has huge capability and flexibility. And coming off of this daughter card here, there are, I used to know this number off the top of my head, like 70 high-speed links which we can leverage for connecting it to other things as and where we decide. And of course you've seen this, 16 of them, put them in here, 3.2 kilowatts NEU, 48 volts in the back, totally liquid cooled. And then when we get a supercomputer and we stack lots of shipping containers together, give you an idea, this is a data center designed out of stacks of shipping containers. That is about the size of one of our ExaScale machines, one of those sheds. But part of the design for an ExaScale machine for us also considers the other 3 sheds. Because you may wish to put your ExaScale machine somewhere where the electricity is really, 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 really cheap. And everyone is going to want to put their pre-processing and storage equipment next to it. So the other 3 sheds are going to be for. So, thank you for listening. I'm more than happy to take some questions now, and please connect to me by going to thecoolingguy.me and sending me a connection request on LinkedIn. Any questions?
Now the whole term EXA has been a subject for debate because people realize that reaching EXA flop is more challenging than we thought. So people now also are referring to EXA as EXA ops. Is that also your definition, or are you still targeting HPC-like workloads?
We still refer to it as one exaflop or equivalent. And the equivalency I mentioned earlier is more about looking at economic benefit of real-world computational loads. That's our trajectory. I think it's cheating to try and redefine an exaflop, but it's definitely not cheating to try and say I want to improve the capability of applications, economy, return on investment, things like this. Right? That's what it's really about.
Just a curiosity, what's the highest natural number you normally use? Or in your simulations, you know, what's that?
I'm a hardware guy.
Natural versus Rayleigh, or
you mean the simulations for the cooling?
Numbers?
For the cooling flow, you mean?
Heat transfer, say,
I am not equipped.
convection over conduction. Just.
So Rayleigh numbers and that's what. Yeah, I don't know that off the top of my head. But if you want to have a chat to some of our engineers that work on all of our cool and flow simulations, I'm more than happy to connect you. I have a few PhDs in that department, and they will happily talk Rayleigh numbers and Nusselt numbers and CFD all day. Okay, so just connect to me, drop me a line on LinkedIn, and I'll connect you to them. Thank you very much.